All right, guys, today we are looking at yet another polar graph, a different type of polar equation. These particular graphs are called lemniscates, kind of another weird word. That's this word right over here, a lemniscate, kind of like the word limousin. Again, the actual names, the words that belong with them, each type of graph, I don't really care so much that you remember the actual name of them. But really, I do want you to know what these look like here. So you'll see these are the kind of general equations for these lemniscates here. You'll notice that all of them have that r squared, and notice it has that a squared value right here. And then we're going to do a sine and cosine of 2 theta for all of these here. So this is the big idea behind the lemniscate, that it all has that r squared. So what I want you to do, kind of what I've hopefully had you do the last couple of videos, and again, I do want you to actually go through and play with them on your own. I know a lot of you are just trying to rush through the videos, rush through like listening to my explanations and my answers, but try to explore them a little bit. That's something that will really help you later on, just to kind of see what kind of patterns you notice, see if you can figure any of this out a little bit more on your own. That's what we would be doing if we were together in class. So use your graphing calculators, or you can use Desmos. If you use Desmos, again on Desmos here, just close these here, make sure you go to that over in the top right here, the wrench, and change it to the polar instead of the rectangular. Here's the regular rectangular grid. Here's the polar grid on that one. So you can go over and use Desmos or use your graphing calculators. Just a side note on the calculator. Really, some of the calculators don't actually connect the graph at the pole. It looks like they don't connect, but they do actually connect. There is, I think, a setting you can change. I think it's in the window, some kind of like a pitch of the theta and stuff. I don't need you to go ahead and worry about that, but it's just something to recognize that for some reason on some of the calculators, it looks like it doesn't graph at the pole, but it does actually connect there. So again, use Desmos, use your calculator. Notice, again, think about how you would graph something with an r squared. So just like when we had like our y squareds, we would have to take the square root. But when you take the square root, it would be positive square root and negative square root. So once you do that, then see if you can fill out, I didn't need to show them all my answers here, fill out the table below here. And I'll come back and we'll look at some of those answers and we'll talk about kind of why that is. So hopefully you took a little bit to graph those on your own. I filled in my answers already just so we could kind of talk through them a little bit quicker and talk through some of the patterns that I wanted you to notice here. Biggest thing right away is the symmetry. You'll notice the cosine graphs all have the same symmetry and the sine graphs have the same symmetry as each other. But it's a little different from the symmetry from our other graphs. Keep in mind that these are all r squareds. The graphs that we were doing before were just r equals. That's why these are going to be a little bit different here. You'll notice that the cosine graphs are actually symmetric to both axes. All of these are going to be symmetric to the horizontal axis and the vertical axis, where your sine graphs are going to be symmetric to the pole. It's not symmetric to either the horizontal or vertical. It's symmetric around the pole. Think about what this compares to. If you remember back to stuff we had done when we were back in school and we talked about symmetry to the origin. What type of equations, what type of functions were symmetric to the origin? Those were odd functions. If we think about the sine graph is an odd function. It was symmetric to the origin. So that can maybe help you kind of recognize that our sine graphs here are going to be symmetric to the pole here. So something I want you to notice, again, when we looked at the general form for these up here, these were all a squareds we thought about it as. You'll notice that the greatest distance from the pole then just corresponds to what we call that a value. So here the a value, it was like 1 squared. The distance from the pole is 1. Here, I know it's a negative. We'll come back and talk about that negative in a minute. But the 9, that would be 3 squared, that distance from the pole was 3. Here's 4 squared, or 2 squared, that distance from the pole is 2, and so forth along there. So kind of keep notice of that. And notice that number of petals is the same for all of them. Technically speaking, usually I don't think we call these petals all the time. We just kind of kept it the same as like our roses. Since these are not roses, it's not really a petal. It's not exactly the same shape as those roses, but it's a similar kind of look to it. So just to kind of be able to talk about them, these all had two. If you notice the shape of all of these were all like figure eights. Sometimes I've heard people say lemniscate figure eight. They kind of have that figure eight shape to it. They rhyme like that. Some people also say they look like infinity graphs here, just kind of that connected eight shape along the way. So they all have the two petals, and they actually all do intersect the pole 4 times. Again, if you think about finding where these numbers intersect the pole, you want to know where is r equal to 0. So if you put r as 0 in, 0 squared is still 0. You're still trying to find where the cosine of 2 theta is equal to 0. Think about where the cosine is equal to 0. Again, that would be at pi over 2 and 3 pi over 2, and then you'd have to keep going 5 pi over 2 and 7 pi over 2, because we'd be trying to find all the numbers between 0 and 4 pi, since we have the 2 theta here. If we divide those by 2, notice we get all of these. So cosine of, 2 times pi over 4 would be the cosine of pi over 2, and that's 0, and so forth. So you'll notice it's actually for all of the cosines, those 4 places where it intersects the pole are all the same. And for all of our sines, those 4 places where it intersects the pole is all the same. So I want to go and look at Desmos just to kind of see how these graphs are formed a little bit. So first off, let me get this back here. If I am graphing, let's do the r as the square root of the cosine of 2 theta. So if I look at the positive square root, and you may have noticed when you did the negative square root, really it just went over that, right? It's the same thing. So realistically, we don't have to necessarily think about graphing the positive and the negative square root, but I wanted you to notice that it really ended up being the same. Again, if you're thinking about r is the distance away from the pole. The negative just says that we're going in the opposite direction. So if we're thinking about it, over here, the distance from the pole is 1. If I had the same distance but negative, that would be over to this side right here, right? So again, since these are, symmetric going back and forth that way, that positive distance and that negative distance are the same. If I look at, now this one, the sine graphs that I have graphed are the negative sine, so the square root of negative sine of 2 theta and negative square root of negative sine of 2 theta. We'll come back and talk about that negative in a little bit, but the same idea. These still are exactly the same graph with the positive or negative, because again, here that distance from the pole is positive 1. If I went in the other direction, that would be negative 1 if I'm looking at, this particular 3 pi over 4 line right here. So again, that's why the positive and negative part don't actually really end up mattering in this one. So let's go back. So I'm going to let's get rid of the negative ones on here just to clear it up a little bit. And let's look at the r equals the square root of cosine of 2 theta, this particular graph here. Kind of our figure 8, our infinity sign here. So I'm actually going to compare it back to the y equals cosine of 2 theta rectangular graph. So again, this is on our polar axes. Desmos actually lets you graph it on both of them here, so are both on the same. So I'm going to kind of keep it there. So when I'm looking at this, if I'm looking at this point right up here at 0, 1, so this point, what it's saying is that when theta is 0, that r value is 1. If we're thinking, again, if you watched the graph that I had done, or the video I had done kind of on comparing the two, that's what we're really thinking about. So we're actually thinking about this as like our r value going up and down on like the y-axis, and the theta value is going this way. So 0, 1 actually corresponds to this point out here at that 1, 0. I know that seems kind of weird, but that's when the theta value is 0, that r value is 1 right here. So if we follow along, this value is getting closer and closer to 0, which means that that value is getting closer and closer to the pole. So what we're doing we're taking the square root of that value. So it actually has a little bit of a different shape than our roses that we were looking at before. But what's important here is if the R value is getting smaller and smaller, that means as I'm getting closer and closer to this point right here, sorry, at pi over 4, 0, at pi over 4, which is this line right along here, the R values are getting closer and closer to the pole. So if I took the square root of it, those square root of it would still be getting closer and closer to 0. So really this part along here essentially corresponds to this first part of our curve here. Now what's interesting is you'll actually notice that there's really nothing graphed between, right here is pi over 4, this line right along here, and up here to pi over 2. There's nothing, no part of the graph that's here either in the positive or the negative direction. It's kind of blank. Think about it right here. From here at pi over 4 to over here at 3 pi over 4, you'll notice that all of those values right here are negative. So this is like, again, that if we're thinking that R value is negative, all right, but if I'm looking at our, actual original equation where it's R squared can never be negative. So what happens is that graph actually takes like a little bit of a break. So I had said from pi over 4 to pi over 2 there's nothing graphed, but we could actually even extend that from pi over 4 all the way to 3 pi over 4. If I'm looking at this green figure 8 here, there is nothing graphed. If I break that off, from pi over 4 to 3 pi over 4, there's nothing graphed either in the positive or in the negative direction. Again, that really just comes from the fact that right here, that value would be negative. And again, we can't have that R squared value be negative. So there's a whole break in the graph from pi over 4 to 3 pi over 4. Then at 3 pi over 4, it picks back up. And that R value, if you follow along with my arrow, that R value once again is getting bigger and bigger, which means R squared is, increasing all the way up to pi where it's 1. So here as I'm, getting further and further away from that pole, it's getting closer and closer to that 1. Right here it's pi and 1 at this point right here. And then if I scoot around here, so up here I was at 3 pi over 4, over here to 5 pi over 4. Again, that was all of this part graphed here. Okay, so that brings us, here we're at 1, then it's getting closer and closer to the pole back here at 0. And once again, we have some break in the graph. Right here at 5 pi over 4 to over here at 7 pi over 4. Again, take a look at what is happening. Let me scoot out a little bit here. Right here, oops, sorry, was 5 pi over 4, and right here was 7 pi over 4. Once again, you can see that that graph has that negative value, and R squared can never be negative. So right here at 7 pi over 4, back up to 2 pi, it's getting further and further away. That corresponds to this last part of the graph right here. Okay, so that's kind of how these are formed. So what's kind of weird about it is you noticed that some of them, if we go back to, our original graphs here, some of them had a negative value in front. So when we look at that, if you think about that negative value, okay, that means if this is R squared, still always has to be positive, right? If that value is negative, that means this value right here would also have to be negative. So let's look at if I have, let's use the, I did a sine graph on this one. Again, you'll notice that it's symmetric to the pole. So this one is the negative right here. So if I'm graphing the sine of 2 theta, just the regular sine of 2 theta, again, right here from 0 all the way to pi over 2, this part of the sine of 2 theta is positive. But if that were positive, okay, going back, let me write it out here. So if you had R equals, or R squared is equal to the negative sine of 2 theta. Again, if this is a negative in front, And if this is positive, a negative times a positive, could that ever equal r squared? No. So wherever that sign is positive, it's not going to show up on the graph. So that's why from 0 all the way to pi over 2, nothing is graphed. Now right here from pi over 2 to pi, again, it goes further away from the pole and comes back to the pole. We have that part of the graph graphed because here along this part of the curve, this bottom part from pi over 2 to pi, that sign would be negative, and a negative times a negative would be a positive, and that's when we can have that r squared value. So again, just to go quickly through it, so here's pi to 3 pi over 2. Again, nothing is graphed on that lemniscate here because again a negative times a positive would give you a negative, and r squared, that's what's important, is always positive. And so that's why we didn't have them here. But then from 3 pi over 2 to 2 pi, again, all of these values are negative, and a negative times a negative is what would give us that positive. So that's why we still do have those values over there, but they're in a little bit of a different place. So if I take off the negative, if you look over here, notice that that's going from 0 to pi over 2, and then from pi to 3 pi over 2, that's graphed. So let's look at how we can actually graph these by hand here. All right, so you'll see that in the long run, these are actually pretty decently easy to graph. I know it doesn't look like it. My explanations tend to be kind of long and lengthy along the way here. But again, I just like you to understand where it's coming from. So if you think about this graph here, you know if that value right here is 25, you know that the greatest distance from the pole, the distance from pole, has to be 5, right? I should say greatest distance right there. Okay, so we know we're going to be 5 away from the pole at our 2, we'll call them petals right here. Okay, so in order for this to be positive, that always has to be positive right here. We've got a positive value right here. We need to know where is this positive, right? We want to know where is that part positive on that one. So in order for us to have that r be 5, that if I wanted r to equal 5, I would need the cosine of 2 theta to equal positive 1, right? Because again, you would have 5 squared is equal to 25 times positive 1. We basically want to solve where is the cosine of 2 theta equal to positive 1. That's where we would find where that basically ends of those 2 petals, those 2 loops are on there. So this is something we know how to solve here. We know we need to go on the interval, not equal to, sorry, just less than 4 pi right here. So if I know I'd need 2 theta then to equal, we want to know where is the cosine 1. We know the cosine is 1 at 0 and 2 pi. Again, it's not going to go to 4 pi because that is not an equal to. Okay, so that means theta is 0 and 1 pi. And that means, again, at 0 and at 1 pi, that's where that r value is 5. That's where that is furthest away from the pole. Again, if you think about it, if I were to plug it back in, you wouldn't have to do this, but if I were to plug it back in, this would be 2 times 0. We know the cosine of 0 is 1, and r squared would be 25. So again, we would know that r essentially would be positive and negative 5. So that would be the point right here and a point right here. At pi, if I put pi in, again, that would be positive and negative 5 as well. We talked about the fact that the negative is just in that opposite direction here. So that is how we create our figure 8 along the way here. Can draw it in. Hopefully yours looks a little better than mine, and we get our figure 8. Let's do another one here. Again, this one, if I have r squared, again, we know r squared has to be positive. Always going to be positive. When we square something, it's positive. So this square root of this negative 36 is a negative. That means This also has to be a negative. Hopefully that makes sense along the way there, that we have to have a negative times a negative to equal that positive. Now, again, we know that furthest distance from the pole, we want to know where r is 6 essentially. Okay, so if we want r to be 6, that means we here want to know where is the sine of 2 theta. This time it's where is it equal to -1. Again, we want the negative because of that negative right here. The negative times a negative would be a positive. Again, we want to know where it's 1 because here that would give us 6 squared is -36 times -1. That's how we would come up with, an equivalent equation on there. So we want to know where is the sine of 2 theta equal to -1. Once again, we want to go between 0 and 4 pi. Let me get a different color here. So 2 theta, we want to know where is the sine equal to -1. We know the sine is equal to -1 at 3 pi over 2. And again, since we're going all the way to 4 pi over 2, I need to find its coterminal. So that would be, I'm sorry, not 4 pi over 2, 4 pi right here. We have to add 2 pi to that, and we get 7 pi over 2. So if we divide by 2, we get 3 pi over 4 and 7 pi over 4. So again, 3 pi over 4, it's going to be a distance of 6 away. And 7 pi over 4, it's going to be a distance of 6 away. So we've got, use the black, it stands out a little better, the 2 loops along here, and we have our graph. Again, it seems complicated. Once you get the hang of it, once you recognize it, that's kind of key. These actually are some of the easier ones to graph, but the key is recognizing it. The nice thing about these is these are the easiest ones to recognize because they all have an r squared. When you see that, again, you know that r squared has to be positive. We know what that furthest distance away from the pole is going to end up being, and that's how we can come up with our values there. So you'll see these in the homework. You'll notice that there's also kind of a mix of some of the other ones. So practice those as well and kind of put them all together and see how you do. All right, let me know what kind of questions you have. Bye, guys.